Hello there. Let's do SDN and SD-WAN, a new and emerging networking paradigm and way of managing our networks. So let's start out with the SDN stuff, or software-defined networking. So first, we need to understand how a network appliance's brain works. So let's grab an appliance like a router. And just like us, you can divide the brain into three parts. Now before you yell at me, yes, we've got the left hemisphere, we've got the right hemisphere, and we've got that little bit in the middle that connects it and the spinal cord together. So technically our brains do have three parts, and so do our routers, and our switches, and our firewalls, and you name it. Now these three parts are referred to as the control plane, the data or forwarding plane, depending on which vendor's textbooks you look at, and the third little one there, and please don't let that size indicate its importance, is the management plane. Now the management plane's primary job is to provide admin control for us, so we can either connect with a console cable or we can remote in through something like Telnet or Secure Shell. Please use Secure Shell rather. And also to provide managerial oversight to the protocols running in the other two planes. Then, with the control plane, its job is to make decisions about how traffic should be handled. Consider this to be a pre-planning part of the brain, where it is thinking ahead and making choices now. And then the data forwarding plane is the part that handles the actual traffic that arrives. And it is making the choices around the current tasks and what needs to be done right here, right now. So with the control plane, it is going to be running stuff like, for instance, OSPF. And that's going to work out all the routes that do exist to all the networks that these routers can discover. And the router will start working out what route would it use to forward traffic to that given destination network. But bear in mind, when populating this routing table, the router has not yet forwarded any traffic yet. It's busy deciding ahead of time. It's sort of like when you're sitting at the office or at school and deciding, what am I having for dinner tonight? You can make that choice before you get to that point in time. Make that decision so that when it comes time to it, you know what to say, you know what to do. It's already been decided ahead of time. So that when the traffic does arrive and the data or forwarding plane has to deal with it, it already knows exactly what to do. Now, in the data plane, it doesn't have a routing table. It has something called the forwarding information base, which is sort of like the routing table, but it's definitely formatted in a way that the router can read and understand. It's more machine code than for human beings. Routing tables are a little bit more for us. Now, in terms of these logical planes, they lead to an interesting problem with a traditional network deployment. So if we have a network like this, where every appliance is running its own local control plane, data plane, and management plane, one appliance in particular, let's say that one, can be absolutely certain about what's going on with itself, its links to its immediate neighbors, and it can sort of trust what it's hearing about from its immediate neighbors with regards to that network or link they have in common. But the problem is, anything beyond the immediate neighbor, that router in particular with the yellow arrow, cannot be sure about what's actually happening. Everything is, as we like to say in routing by rumor. So that router's insight into the rest of the network is a little bit obscured. It sees less than it would like. It only knows about that network there, that one there, that one there, that one there, and that one there, and these appliances here because of what its immediate neighbors have told it. But because of that, it is unable to have real-time accurate information about how the network is performing. So this router's control plane, in particular, can only be sure about what it's got a close connection to, and everything else it has to rely on probably out-of-date information and possibly inaccurate information. If you decide to pursue networking further, beyond something like Network Plus, and do CCNA or anything like that, and go further than that even, you're going to start learning about weird methods that these routing protocols use to try and overcome these issues around the local and immediate knowledge and the remote knowledge being possibly imprecise and a few seconds out of date. So this is where SDN, or Software Defined Network, comes in. So what's going to happen is we're going to deploy an SDN server. And this SDN server runs a virtual network-wide control plane. And obviously the server is connected somewhere here, but arbitrarily it doesn't really matter, because all of the appliances are going to give up their local control plane, mostly, and rely on that virtual network-wide control plane running on the SDN server. Now, the appliances do maintain a little bit of a local control plane, but for the most part, they are relaying their information to one central server. And this allows this one SDN server to be able to see how the network is doing, what's going on, what's the status of links, what's the traffic like, or congestion like for that traffic, should I rather say. And it can pretty much see everything. But besides that, this SDN server is also able to apply logic to the network and decide how the traffic should move forward, packet by packet, session by session. So just to give you a quick visual, we can have the first packet arrive on an SDN enabled router. That SDN enabled router will then go and ask the SDN server, hey, how should I forward this traffic? And the SDN server can then instruct all these routers to forward the traffic along this pathway. Then when the second packet arrives for the same session, that router that it arrives on can go and ask the SDN server, hey, do you still want me to forward this through the same route, or do you want to change it up? And due to congestion or something like that, the SDN server might instruct that particular packet to use a different route through the network. And then when the third packet arrives for the same session, same again. That router can ask the SDN server, hey, how would you like me to forward this? And it can instruct these routers to forward the traffic along a completely different pathway. So that's pretty damn awesome. Let's look at some of the characteristics and properties of SDN networks. So first of all, software-defined networking is defined by the IETF's RFC document 7426. And it brings along several major advantages. First of all, we can have a central policy management approach to how our network is going to behave. We can define how the network should operate, and we can give the network a set of goals. And what's going to happen is the SDN controller is going to work out how best to achieve those goals. Now, those goals can be everything from guaranteeing a certain amount of bandwidth to keeping certain services at a certain latency or below, sacrificing other services. There's a whole lot of cool things, but the SDN server can have a little bit of autonomy in making decisions on how to achieve the desired state and the desired performance of the network. And what's also quite cool as well is these policies can be adjusted on the fly and even set to be applied based on certain triggers and thresholds being reached. Another cool thing is SDN is transport agnostic. It doesn't really care that much about the underlying network technology. It only pays attention to how is that particular pathway through the network performing. What's it doing? Is it able to meet the needs of the traffic and the specific service? Its only concern is transporting the traffic. That is it, and meeting those goals. Another cool thing as well is we can do something called zero-touch provisioning, which means minimal to zero direct administration of the network appliance itself. Once enrolled on an SDN server, the SDN server can push all config and instructions through to the network appliance, meaning the most we have to do is physically install it and maybe something to enroll it. But once enrolled by an SDN server, zero direct administration has to be done on the appliance, which means network management can be done centrally from head office or something like that. And as I've been saying, or at least alluding to, it is application aware. The SDN controller can receive input and directives from the applications themselves to adjust the network performance, in addition to us administrators telling it, I want the service to perform like this, that service to perform like that. It's very, very cool. Now, in terms of how SDN architecture is applied to our networks, we break it down to three main layers: infrastructure layer, control layer, and application layer. Now, down at the infrastructure layer, that's where we will find our various network appliances, whether it be a router, a switch, a wireless access point, a firewall, you name it. And then at the control layer, that is where our SDN server will sit. And between these two, we'll have something called a southbound API interface. Essentially, a variety of protocols and services that an SDN controller can use to provide instructions and get feedback from the appliances. Amongst them is SNMP, but there are a bunch of other protocols and services that can be used, but that may vary by network vendor. Then, at the application layer, will be the services and applications that we are requesting, whether it be a directory service, a web service, an email service, or a database service. And they can communicate with the SDN controller and say, hey, I need a bit more bandwidth, or you know that bandwidth you gave me earlier, you can take it back again. And they communicate with the SDN controller through something called a northbound API interface. So as long as you remember that in the infrastructure, the appliances are at the bottom, and the applications are at the top, and the SDN controller is in the middle. And that will help you remember the whole northbound, southbound thing. But we can take this a step further with SD-WAN. And you guessed it, software-defined WAN. Now, SD-WAN is trying to solve a problem with traditional WAN connectivity. Let's draw it out, and you'll see what the problem can be. So we can have head office and a couple of branch locations. We might have our data center hosted somewhere else. And like most modern organizations, we'll probably have some cloud instances running in our environment. And who knows, we might even have some external partners we work very closely with. Now, all of these sites and locations are going to have to be connected together. We can use the ordinary public internet and have a bunch of fiber to the home, fiber to the business, fiber to the whatever connections. Obviously a couple for our head office for reliability purposes. But we also might be using a more private WAN solution, such as MPLS, to connect some of these locations together. In some cases redundantly. We might even have some cellular connectivity, just as a failover to the ordinary internet. And then, who knows, maybe this organization's been around for a while and still has a load of leased lines. Although leased lines are very slow, they are dedicated direct connections that are normally operated by a service provider, but provide connectivity only between customer sites. The benefit to the customer is they get exclusive access, so those slow data rates that leased lines offer aren't so much of an issue when the latency is very low. Now, why is this a problem? Well, first of all, these are going to be operated by separate WAN or internet service providers, and we have to manage them all separately. And because they are managed separately, operated separately, and oftentimes configured separately, even on the client side, it can be very difficult to get these connections to work together redundantly and spread workload between them all. This is where SD-WAN comes into the equation, or software-defined WAN as we've already defined it. It is based on software-defined networking, except now we're applying it more to WAN management and connectivity options. And what it can do for us is it can help us consolidate disparate WAN links into one management platform. This is obviously going to simplify management. It's going to allow for WAN links to be used in conjunction with one another. So I can actually have some traffic maybe going through a fiber connection, other traffic going through an MPLS connection, all to the same location. We can have load balancing, redundancy, loads of cool benefits here. So let's look at some of those major benefits. We can have, similar to SDN, goal and intent-driven automation of our WAN and route selection through the internet. And application services, just like with SDN, can also feed into the SD-WAN controller's decision-making process to make choices about how traffic should be forwarded and what should be done in disaster events and emergencies to deal with potential failures of WAN connectivity, which means we get improved availability. So taking this and applying it to this crazy management problem we have, essentially this organization with their headquarters, branch 1, branch 2, data center, cloud, and external partners can view their network administration for WAN connectivity as just SD-WAN to describe both the private WAN and the public internet. Each location or site will see one major connection to this logical WAN that is being managed by the controller, and that logical WAN link is being facilitated through the variety of physical medias, fiber, MPLS, cellular, leased lines, etc. So we get a lot of cool consolidation and simplification of our management. Yet still underneath it, just like with SDN, it doesn't really worry too much about how the actual infrastructure works underneath. It's still going to have all of that crazy chaotic cabling and different services, but it does simplify the organization's management of their WAN connectivity. Now, if this sounds awesome to you, and trust me it is, well, there are a few considerations that we need to bear in mind before we run headfirst into SDN and SD-WAN. So looking at those considerations, older appliances may not support SDN and SD-WAN. Even if we do a software upgrade, the hardware might not be capable of it and at some point a network vendor will end of life that appliance and stop supporting it. Now, the reason why this might be a problem for many organizations is most enterprise environments will want to keep enterprise equipment working for as long as possible. Once it's made its return on investment, as it continues to operate, it's just saving money. And an old router or an old switch, as long as it's keeping up with the needs of that portion of the network that it serves, there's no reason to go and replace it just yet. There are organizations out there that are still using network appliances they bought before I started my career in IT. And they're still serving a function within that organization's network to this very day. Admittedly, maybe not in the same role or capacity they did when they were first bought, but they still keep up with some portion of the network's needs. So that's one problem. Next up, it is still early days, relatively speaking, for SDN and SD-WAN. Now, the reason why this is a big issue is because the network industry moves very slowly compared to the rest of the IT industry. If you get into software development, it moves at a rapid pace. You get into cloud, it moves at a very rapid pace. What you learn today might change in a year or two's time from now. But with networking, what you learn now is going to serve you for a really, really long time. Because if networking is to IT operations as roads are to a city, you can't rip up the roads and relay them overnight just because there's a new type of material we can surface the roads with. So networking evolves pretty damn slowly, but it does evolve. Although we are at a point right now where we are expecting to see a lot of major innovation and improvement in networking, it's taken many, many years to get to this point. Another issue with this is that the vendor interoperability with SDN services is quite uncertain. You might come across vendors that offer interoperable SDN solutions, and then you might have some vendors where you've got to buy their equipment, their SDN controller, and there is zero interoperability with other vendors. It hasn't really had enough time yet to mature into a proper open standard like something like, for instance, OSPF, RIP, or anything else like that has been around for ages and guaranteed to work the same way no matter the vendor. The commands might be different, but once you learn some of these protocols, they operate the same way on the network regardless of the vendor it's running on. And as networking evolves very slowly, it will take time to get used to this new administration and management paradigm. And believe you me, administrators that have been able to get away with not having to evolve and upgrade and update their knowledge and skills too rapidly might resist this change a bit. Just look at how the IPv6 migration is taking forever. And then there are some security concerns as well. This new paradigm for network administration means that some people deploying SDN solutions will just be relieved to get it working, and they will not want to do anything to secure it because they're going, don't touch it, it's working, don't mess with it. But you can't sit back on that excuse forever. At some point, you do need to look at your cybersecurity because attackers are always looking for an easy target. And a poorly deployed and poorly secured SDN solution might be just the right option. It's new, it's relatively young as an open standard, and you might have some vendor proprietary implementations that could have vendor proprietary vulnerabilities and exploits. But generally, the controller is the biggest issue here because it is a high-value target to the attackers and they will aim at it. Especially because if they can control the SDN controller, they've got your network now. It's just the endpoints they've got to get to. But I don't see that as too much of an issue because if you go for a full SDN solution, then you know that's the one thing you really need to focus a lot of your security on when it comes to preventing administrative control of your network being taken over from you. Compare that to traditional networking where every appliance runs everything locally. You've got to make sure each and every one of your network appliances is equally well secured. All you need is one that's not well secured for the attacker to get in. At least with the SDN solution, it's one place to watch and monitor for your security, and if you lose control of your network, you can be pretty sure exactly where the attacker is. Nonetheless though, SDN and SD-WAN are pretty awesome and exciting technologies and are starting to gain some significant momentum right now. So this is definitely something you want to look more into and maybe develop your skills and knowledge here if you are going to consider pursuing something beyond just CompTIA's Network Plus. But that is all you need to know about SDN and SD-WAN for Network Plus. It is an introductory topic. in this syllabus. So hopefully we managed to lay some good foundations for you to build on for this. Otherwise though, I'd like to say thank you for watching. I really appreciate it. And if you have any friends, family members, colleagues, peers, or anyone like that who is also interested in doing CompTIA Network Plus, don't be afraid to share this video with them. Otherwise though, I will catch you in the next video.